my name is Walter, Wally for short. I live in a frat house, Kappa Sigma Aqua, with my best buds. We are all water molecules. We are really a close-knit group. We have bonds called H-bonds, short for hydrogen. These bonds give us certain properties such as high surface tension and low vapor pressure. We have a lot of fun together. We have some great parties where a lot of interesting things happen. A lot of couples come to our parties, but soon they separate and mingle. Certain compound couples, especially all of the ionic ones, are known for their flirtiness. We call these electrolytes, and they conduct electricity. Strong electrolytes ionize completely and conduct more electricity than weak electrolytes that only ionize partially. Non-electrolytes do not ionize at all. When we have parties, we, the water molecules, are known as a solvent, and our guests who dissolve into our parties are known as a solutes. Together we form a solution. When these parties are held at our house, the water frat, the solutions are known as aqueous. The administration has a maximum capacity for our house. The ratio of the compounds to the water molecules is called the concentration. When we reach maximum capacity, it is called saturated. At this point, we can't let anyone else in. However, sometimes we defy the rules and manage to squeeze in some more compounds. This is called supersaturated solution. If the campus police come, people panic and a precipitate is formed of the excess gas, the solute, in our house. We can define concentration in a few ways. A lot of people are curious to know what our parties are comprised of. The three ways we describe concentration are in molarity, molality, and in a mole fraction. The way people behave at our parties changes with seasons. At summer parties, guests come to our water parties tend to be very excited and jumpy. They move around a lot. Sometimes they bump into each other. When we hit a certain temperature, everyone goes berserk. They stop hanging out with other guests and start running around the room. This temperature depends on the molality of our parties. Remember, molality is the amount of guests divided by the total mass of everyone present. If we have more guests, this boiling point temperature is higher. In the winter, the opposite occurs. People at our party get so cold that they can barely move. They form a solid. The temperature at which this occurs is the freezing point. Similarly to the boiling point, when more guests come to our parties, the freezing point changes. In this case, the more guests we have, the lower the freezing point, because it is harder for us to form strong bonds with so many people we don't even know very well. These changes, which depend on the amount of guests at our house, are called colligative properties.
The name's acid, acetic acid. You can call me vinegar if you prefer. I am the president of Acidia. Sodium hydroxide here, Lie for short. I'm the dictator, benevolent leader of the great nation of Baseland. Our countries have been rivals for eons. Unfortunately, our borders are slightly indistinct, to put it mildly, which makes it rather difficult to engage in warfare. Many compounds in the area don't even know which country they're a citizen of, if any. Both our nations encompass various regions with different landscapes, climates, and cultures. We do know a few properties of the residents of Acidia. Acidians tend to taste sour. We are electrolytes, meaning we conduct electricity. We cause some indicator solutions, such as phenolphthalein, to change color. And when we meet some metals, we react together to produce hydrogen gas. And when we meet the residents of Baseland, we usually form water and a salt. The citizens of my country taste bitter. Of course, in a civilized nation such as Baseland, cannibalism is frowned upon. Don't get any ideas. Anyway, we tend to distort the truth a bit, so some call us slippery. Like acids, we are electrolytes, change the color of indicators, and we form water and a salt when we react with acids. But all these properties of a citizen of Acidia or Baseland are specific and don't provide a firm definition for who is an acid and who is a base. Which is why we've come here to the neutral territory of Waterstan to negotiate a treaty which will once and for all decide who is the citizen of Acidia and who is the citizen of Baseland. The author of the first proposal, please explain it. I am Savante Arrhenius, and I believe citizens of Acidia are compounds which ionize to yield hydrogen ions in aqueous solutions. When citizens of Baseland ionize in aqueous solutions, they yield hydroxide ions. Could you provide an example using one of my nation's citizens? Oh, of course, Mr. Vinegar. Let us use the example of hydrochloric acid. Hydrochloric acid is composed of a chlorine atom and a hydrogen atom. By my definition, the Arrhenius definition, hydrochloric acid is an acid because when it is placed in water, a hydrogen atom is released from it, combining with water molecules to form a hydronium ion. Well, that's great, but if I'm hearing you correctly, it seems that one of my upstanding citizens, ammonia, isn't a base under your definition. Ammonia doesn't even yield hydroxide ions in aqueous solutions. It doesn't include an oxygen atom at all. Well, my definition does have some minor defects. Nothing's perfect after— Next! Hello, I am Johannes Bronsted. And I'm Tom Larry. And we'd like you to present with what we think we know is a far superior citizenship requirement than that of Mr. Arrhenius over there. Our definition is also simpler. Here it is. An acid donates hydrogen ions while a base accepts hydrogen ions. That's it? So I guess good old ammonia would be a base under your definition, actually, because it accepts hydrogen ions from the water molecules in a solution, forming ammonium, NH4+. Well, that's good. But wait, wouldn't water be an acid because it donates the hydrogen ions to ammonia under your definition? Well, that's right. In fact, you can write out the dissolving of ammonia in water as a chemical equation. You'll see in this equation that hydroxide is actually a base. In fact, I like to call it a conjugate base because it's paired up with water, the acid in the reaction. The ammonium is a conjugate acid in the reaction to ammonia, the base. Wait, I'm sorry to interrupt, but I couldn't help thinking that because, for example, sulfuric acid, one of my country's citizens, donates hydrogen ions to water when it dissolves, wouldn't water not only be an acid, but also a base under your Bronsted-Lowry definition? Well, yes, isn't that awesome? Not if we want to know which country water is a citizen of. Next! Hello, I'm Gilbert Lewis. Yes, Gilbert Lewis, the discoverer of covalent bonds and the man who named the photon. My classification system for acids and bases is by far the best. Well, what is it? Acids accept electron pairs, while bases donate electron pairs. That's it. Well, is it just me, or is that suspiciously similar to Bronsted and Lowry's definition? In your definition, bases donate electron pairs, and theirs, bases accept protons. It's basically the same thing. Well, to be fair, I came up with my definition without knowing about Bronsted and Lowry's work. You can't blame me. That's no excuse. Your definition seems to have some major problems. For example, under your classification, every cation would be a citizen of my nation of Acidia, and every anion would be a citizen of Baseland. Right now, only compounds live in our countries. If we follow your definition, we'll have serious overpopulation problems. But my definition is more generally applicable than those other two. Please at least consider it. Next. Wait, are those the only 3 definitions? None of them was all too good. Well, I suppose we'll have to use the Bronsted-Lowry classification and the Lewis classification together with our own judgment, depending on the situation. It's not that great. Well, that is disappointing, but do not let a lack of substantial progress prevent us from conducting the next important order of business, the census. Oh yes, the census. I forgot you were not familiar with the city and Baseland, viewer. You see, not only do we have trouble distinguishing who is a citizen of which nation, but we also have no accurate way to measure the concentrations of our nation's cities. We have serious problems, as you can tell. All we know now is how to determine how acidic or basic our solution is, or our city is, but not how concentrated it is. We measure acidity using the pH scale. Remember how Bronsted and Lowry's definition said acids donate hydrogen ions while bases accept hydrogen ions? Well, pH measures the number of hydrogen ions in a solution. Specifically, we take the negative logarithm of the molality of the hydrogen ions. Well, for example, let's say there are 1 times 10 to the negative 4 moles of H plus per liter of a solution. So then we take the log of that, base 10, which gets us negative 4, and then we take the opposite of that, which gives us a pH of a solution is 4. The pH of pure water is about 7. Basic solutions have pHs higher than 7, while acids have pHs lower than 7. Water is a neutral solution. Well, this is all great, but we need a way to find concentration, so we've decided to solicit ideas about how to measure the populations of our cities. Does anyone have a method we can use in the audience? Anyone? Wait, what's that I see in the distance? Is it a bird? It's a limiting reagent. No, wait. It's a polyatomic ion. No, it seriously is a bird. Wait, it's closer. It's Chemist Man. Thank you very much. I will be signing autographs later. I am Chemist Man, and I am proud to present you with my system, titration. Well, that sounds fun, Chemist Man. What is titration? Titration is my awe-inspiring method of finding out the concentration of an acidic or basic solution. First, I would like to introduce my sidekick, pH Indicator. Hello. pH Indicator changes color depending on the pH of a solution. He will help us later on. This is because when, as I'm sure you all know, when an acid and base are mixed in a solution, they form water and a salt. This reaction where the reactants are an acid and a base is known as a neutralization reaction, and neutralization is the key to my method, titration. Let me explain how to do titration. We begin with a beaker or a flask if you prefer, containing either an acidic or basic solution with a known pH. We then add a pH indicator to the solution, just a few drops. We set up a burette containing a solution of the opposite acidity into the flask with a known with a known concentration. Then, drop by drop, we drip the burette solution into the flask solution very slowly. At a certain point, the acid and base will neutralize. This is what we like to call the equivalence point. When there are equal amounts of hydroxide and hydrogen ions, pH indicator will change color. When we know the amount of burette solution required to neutralize the flask solution completely, the concentration of the burette solution and the pH of the flask solution, when we know all that, we can determine the concentration of the flask solution with several calculations that you will learn soon. Wait, that's it? Yes, that is it. That is titration. I will be off. Look for me next time. Remember, I'm Chemist Man. Thank you, Chemist Man and pH Indicator. So it seems at least the problem of determining concentration is solved. Well, yes, it certainly is. By the way, Vinegar, I was wondering, would it be okay with you if our country stopped fighting wars like we've been doing since as far as we remember? You know what, Lai? That sounds great. Let's be friends. And they lived happily ever after.